Hi data junkies, welcome back. We're continuing our journey into the two-sample hypothesis testing with the Z and T tests, and in this topic video we're going to talk about non-parametric tests, specifically the Mann-Whitney test and the Wilcox rank test. So again, we're going to look at the non-parametrics. After this, we're going to be looking at two-sample t-tests for proportions, and then the future videos are going to be looking at evaluating effect size and power for two-sample testing. So let's go ahead and get started with the non-parametric, the Wilcox rank test. So first of all, let's take a step back and ask, non-parametric? What is this thing called non-parametric? Well, parametric are the majority of the tests that we deal with, and those are when we have dependent variables that are interval or ratio data. There are numerics, or quantitative measures. Non-parametrics are for ordinal variables, the categorical ones, not nominal, because nominals don't have any ranking to them, but the ordinals do. Now, keep in mind, parametrics have things like means and averages and standard deviations. Well, means and averages are the same thing, but means and standard deviations. But when we deal with the ordinals and the rank groups, we're switching gears to the median. And the median is where it's at for the non-parametric tests. Now, keep in mind, a slight caveat is that when we're using medians instead of the means when we were building our confidence intervals, that it can be more sensitive to things like our sample sizes, and so our intervals could be artificially wider than they might normally be, particularly when our sample sizes are small. Let's go ahead and talk about a few of the pros and cons versus the non-parametrics to their parametric counterparts. Non-parametrics, some of the benefits include that you don't have to worry about data requirements. Things like normality and homogeneity, which is a fancy way of saying equal variances. So we don't have to be concerned about things like the distribution of the variable. They're also easier to calculate. You can do them sort of on the back of the napkin sort of paperwork there. Whereas there's a few cons as to why we don't do non-parametrics, because with such advantages as not having to worry about variation and normality, that it seems like they'd be very attractive, especially if they're easy to calculate. But unfortunately, they're less powerful, they're less accurate, and they're less specific. And I'll be sure to talk about why we go into each of these in detail. But with the less specific, let me point out now that when we go ahead and determine if we can reject the null hypothesis or not, we aren't always as clear as to why it is that we are rejecting it. Is it due to differences in the medians conversely to the means? Is it due to differences in variation of the data and standard deviations, or IQRs? And so it's a little more cloudy when we do get to have our decisions as to why we're doing it. But let's go and touch briefly on the less power and less accurate part. Now, in order to understand this, we have to understand that we could also use numeric variables in non-parametric testing. However, when we do so, they're going to be converted to ranks, and they're going to be treated like ordinal data. And we're going to see how this works in an example here. So we could imagine that we have a small group of people, and we're asking them how many posts do they have to Instagram this month, and we have it by gender. We have 6 men and 6 women. The 6 men have ranges such as 75, 68, 53, 44, 35, and 30. The women have ranges such as values such as 114, 88, 68, 42, 28, and 21. These are numeric counts, an exact number of how many posts they had to Instagram that month. So this would normally qualify for interval ratio variable. And we can see when we take summary statistics of these that the average of men is 50.833 posts and women is 60.167 posts, with a mean difference between them, this is an unstandardized difference, of 9.33 posts per month, with women coming up with more posts to Instagram than men. Now, when we go ahead and put this into sort of a data frame view, a spreadsheet sort of view, we can group them together and then we can sort them where the highest posts are up at the top. Then we can go ahead and add another column to them where we've ranked them, where the highest number of posts that month is the first rank, the second highest is the second rank, third highest is the third rank, and so on, until we have 12 ranks, one for each of the 12 people in our data. And what we then find is if we take a mean of the ranks, men come up to be ranked 6.5, and women come up to be ranked also 6.5. Well, that's curious. A moment ago, we just saw how women had a higher average than men. And it was a fairly clear difference between the averages. It was a difference of more than 9 posts. But here, when we put it into the ranks version, it becomes a little more cloudy, a little less clear. And this is part of how I want to illustrate to you that when we go ahead and switch into using medians instead of means with the non-parametrics, that it can be slightly less powerful and less accurate in its results. And it really complicates things in situations like this, where the ranks happen to balance themselves out, or in instances of what we call ties, where things share common ranks, like they're both ranked 2, both ranked 3, things like that. So, when would you want to use a non-parametric version over its parametric counterpart? So, essentially, when your dependent variable is ordinal, and you should normally have it as interval ratio, but it just so happens to be that your dependent variable is ordinal. We're learning about t-tests and z-tests, and they require interval or ratio dependent variables. But if you're running something on a Likert scale, then that would more likely favor the non-parametric counterpart. Now, I have said in the past that we can sometimes squeak through ordinals with many categories through as if it's interval or ratio, but ideally it is the non-parametric counterpart that they should be properly used. Another reason we might want to use them is when the dependent variable is interval or ratio, but it's highly skewed. The more skew a variable has, dependent or otherwise, the more skew a variable has, the more we would want to have a higher sample size for it to help compensate for the skew. However, if the skew is bad enough, regardless of sample size, we can go ahead and put it into a non-parametric version. And if you want to check this visually, I recommend using box plots. It's a great tool to kind of understand where the spread of your data is. Do you have to deal with outliers? Is the median somewhere in the middle, or is it skewed off to a side? Where's the box fitting in that box plot? So as you're taking a look at this and you're examining the spread, keep in mind that t-tests tend to be fairly robust against parametric violations. And what do I mean by a parametric violation? Well, I mean that the sample sizes for the two groups that you're looking at, N1 and N2, when they're relatively equal and relatively large, then you're going to get fairly accurate results most of the time, and you can go ahead and use the t-tests, even if you're concerned about some of these potential violation issues. The t-test would be fine, and it can hold up. It's a tough cookie. Otherwise, if you're concerned about it, default to the non-parametric version as a more conservative approach. So keep in mind that for this course and for the purposes of statistics right now, what I want you to take away is to know the concepts of these non-parametrics. Know when and how to use them, and how to do them in R. We're not going to go much into the math of the non-parametrics, because while they're easier to calculate, they can be a little more labor-intensive than I'm going to need you to be doing right now in class. So, again, just go ahead and focus on what are the non-parametrics, what are some of the characteristics of them, and know when to use them. And then, of course, how to execute them in R. So let's go ahead and discuss the two different types of non-parametric t-tests that we're going to be using in R. This is going to be the Mann-Whitney U-test and the Wilcox and rank sum test. Now, first of all, I just want to get off the table that these are essentially the same tests. They use the same function in R, and they were developed relatively around the same time, but just happen to be by two different groups of statisticians, and there might be some bickering in the statistical areas of which one actually came first and who was right about which, but we're not going to worry about that. Just understand that the Mann-Whitney U-test is when you deal with your independent samples, and there's an option inside the function that we're going to have as paired equals false, because it's an independent sample. And in R, it's going to give you a W statistic. But depending on where you go, other software doing things by hand, you may see it appear as a U statistic, which comes from the original formula. And you're going to use this W or the U instead of a T. And we'll see what this looks like in the output when we do an example here. The Wilcox rank sum test is the exact same process, except we're going to use it for paired tests, and we're going to switch that option in the function to paired equals true, or paired equals T. And again, it's also going to give you a W statistic instead of a T. What we're looking at here are income groups from the General Social Survey 2016, and it asked the question of the survey taker, how much income did you make over the past year in 2015? And so we have 26 categories of potential buckets of income. It didn't ask for specific dollar amounts. That was thought to be a little too sensitive. So they created these ordinal buckets in which to code someone's individual income. And so we see that represented here with the categories and then the frequency counts for each particular category. If I go ahead and put this into a histogram mode, yes, histograms are typically for numeric variables, but there are 26 income group categories, so I'm feeling pretty good that I can go ahead and chart this out as if it was numeric in order to get a sense of the shape of the data here. And we can see that it definitely has some left skew going on here. Not something you normally see when you're looking at salary income. Typically it's got right skew. But in this particular data set here, could be the way they had the buckets coded. It could be that they have a large number of low income buckets relative to the medium income buckets. We could take a closer look at that, but what I generally want you to see here is that it is a histogram shape. And if you're looking at the code at the top of the screen, I did an as numeric on income in order to use the integer variables because this is a factor, and I'm not using the categories in order to generate out the histogram plot here. And the dots I have up at the top are just indicating that I have extra code I'm not showing on the screen where I cleaned up the plot a little bit, such as giving it a title and giving it access labels and giving it a light blue color. And if I want to go ahead and split this up a little bit, I have two overlapping histograms here where they're split up by gender, and the women are this sort of orangey pink color and the men are sort of this purpley blue color. And you don't see them so much distinctively because there's a lot of overlap where we have this more purple hue going on. But what we can start to see up at the top is that men are peeking up over the top and to the right a little bit, and women are definitely up at the tops on the left side here. And let's go ahead and take a closer look at this actually numerically. So now I'm going to go ahead and look at their medians because these are non-parametric tests and they're going to look at the medians. And if I look at the median income for men, it says that it's income group number 19. Now keep in mind this isn't 19 like $19,000 or $19 even. This is the number of the group that as numeric on there is getting rid of the text labels and looking at the integer values. So this is income group 19. And if I look at the women, their median income is income group 18. And to find out what those actually mean, we need to go back and look at those qualitative labels. So I'm going to use the levels function on the income variable, and it's going to print out the list of the different levels. And all the way to the left side there, in the square brackets, that's a printing row reference. So the first one refers to the under 1,000, then level 2 is 1,000 to 2,999, then it goes to the next row with 3 to 3,399, and so on. And so I can look down this table here to identify where I can find income groups 18 and 19. Income group 18, the median for women, corresponds to 40,000 to 49,999. And men, the median income group of 19, comes out to 50,000 to 59,999, which could be, depending on your range, anywhere from a couple dollars up to almost $60,000 in difference, depending on where people identified. If you're looking at this to the midpoint, it's about a $10,000 difference between these income groups, which is nothing small when we're talking about potential wage gaps in society today. So let's go ahead and actually run a test here in R to see if these two groups are actually statistically significant from each other by their rank. So when I do the Mann-Whitney test, I'm going to set it up with the Wilcox.test. Now it's called a Wilcoxon, but we call it in R just Wilcox, W-I-L-C-O-X, .test, all lowercase. Then inside there you go ahead and specify your dependent variable, and then tilde your independent variable if you have it set it up by groups. Otherwise you can use any of the other sorting and filtering methods that you use for a t-test. But in this case, in the example here, I have it just sorted out with the income group, tilde, your categorical group. And note, I'm keeping the as numeric on there. That way it takes that ordinal factor and converts it into a numerical integer that it can go ahead and use in the tests. And when I do the Mann-Whitney test, after the variables, I'm indicating paired equals F or paired equals false, so I can do an independent samples. Now the Wilcoxon rank sum, this is not correct because the way I show it is that it's paired equals T for paired samples. And the data here is not actually a paired sample, but I wanted just to show you the code on how it would look if it was. So when I said that it's wrong, I'm referring to the code itself is not actually paired data, but that's just how it would look if you were to run it as a Wilcoxon test with paired data. Otherwise, use the paired equals false to do the independent samples. And the results are generally going to be exactly the same. And with the Mann-Whitney test here, it's going to tell you it's doing a Wilcoxon rank sum test Don't worry about that. You're getting the Mann-Whitney results so long as you specify that the pairs were false. It's going to give you the W statistic, and in this case the W statistic is this gigantic number. In this case it's 912,260. Don't worry about that. And it's just look at that and the p-value. So when you do your reporting, you would say that you performed a Mann-Whitney U test with a W statistic of 912,620, and that your p is less than whatever your alpha is. In this case, it's going to be incredibly small. There are additional features and options that you can add into the Mann-Whitney U test and the Wilcox and rank sum test, in which you can turn on features such as confidence intervals and getting precise estimates in there. So check out the exploration options or the script code that corresponds with this lecture talk, and you'll see some of the options there that you can turn on and off. But otherwise, if we want to go ahead and conclude this, we would say that men are ranked higher by median income group than women with the W statistic of 912,620. And in this case, I'm using a p-value less than 0.001 because I really want to indicate that it's a small value, but I'm not going to do a p equals because the p-value is too small to report using scientific notation. And with that, I'll see you all in the next video where we talk about proportions.